All right, so hello everyone. It's 8 a.m. in Los Angeles, and this is the first week of March, which means that we have our first edition of Spring Quasi-World Seminar. And our speaker today is Mario Bonk with a talk Elliptic integrals, modular forms, and the Weierstrass zeta function.
Yeah,
So,
thanks, Misha. I think some of you will have noticed that the title of my talk has changed. So originally, I wanted to talk a bit about a different topic, namely some ongoing joint work with Zhishang Li and Wenbo Li. And we were hoping to have the paper ready by this time. But, well, in our proof of our main theorem, I mean, we still have some loose ends. And I decided that it's at this point a bit too early to talk about this paper. So I decided actually that I will change the topic of my talk for today. So yeah, so my topic is elliptic integrals, modular forms, and the Weierstrass zeta function. So this talk actually, I've given this talk before, namely it's essentially a colloquium talk at the University of Washington, but I think there is very little overlap between these audiences. So I thought it's a good idea to give this talk again. I should make a disclaimer, namely, this talk should have been given more than 100 years ago. So what I will talk about today is really nothing new. So it's all known, but I think it's fair to say that what I will talk about is not well known. Okay. All right, so let's start at the beginning. So let me give you a quick outline here, what is going on. So I should say that my talk is based on a recent paper that I wrote about the quasi-periods of the Weierstrass zeta function. So you can find this paper even either on my website or on arXiv. And this will appear in a Swiss journal, actually, L'Enseignement Mathématique. So let me give you an overview of what I want to talk about today. So we'll give you a very quick introduction to periodic and doubly periodic functions. And then I will tell you about some very classical subjects, namely elliptic functions according to Weierstrass. And then I will get to the main player today, namely the so-called Weierstrass zeta function. And I will formulate a problem. And in order to solve this problem, we have to make an excursion to some related themes, namely Eisenstein series and modular forms. And then I will formulate my main result. The main result is actually about a very specific conformal map. And my result is that one can give an explicit, very geometric description of this conformal map. In order to prove my theorem, I will have to talk about some other very classical themes, namely the hypergeometric ordinary differential equation, Schwarzian derivatives, and Schwarz triangle functions. And well, this will then lead to the proof of my main theorem, and then I will make some concluding remarks and discuss some further directions. So let's get started with all of this. Yeah, let me try to get rid of this picture here. So let me quickly remind you of what periodic functions are, right? So if you have a function, and the function that I will consider today all live on the complex plane, then you call a value a period of the function, well, if the function doesn't change if you add the period to the argument, right? So if you have a function that has non-zero periods, I mean, then you call it a periodic function. And it's immediate to see that the set of all periodic functions, of all periods of a function, actually forms an additive group, right? So this will be an additive subgroup of C. So we know, of course, some basic examples. I mean, trigonometric functions are periodic, right? So the sine function, for example, will have its periods all the integer multiples of 2 pi. Little more surprising, I mean, if you see it for the first time, of course, now we are all used to it, is the exponential function, right? That has periods that are integer multiples of 2 pi I. And if you look at functions like this, namely analytic functions, meaning holomorphic or meromorphic functions, then one can make an additional observation, namely the periods of such a function have to be a discrete subgroup of the complex plane, right? So this easily follows from the uniqueness theorem for analytic functions. So one can now look at these discrete subgroups of C and investigate what they look like. And they come in three forms. There's the trivial case where the subgroup just contains the zero element. Then there's this rank 2 case that we have essentially just seen that arises for periods of trigonometric functions, namely when the discrete subgroup just consists of multiples of some integer multiples of some number omega. And then there's the more interesting case, namely the rank 2 case, where you actually have two generators that are linearly independent over R, and these, what I call omega 1, omega 2, generate a rank 2 lattice. Yeah. And well, given this classification, it's now a very natural question to ask whether there are actually functions that are doubly periodic in the sense that the period set consists of such a rank 2 lattice here. Yeah. And well, I mean, the answer has been known for essentially 200 years. So this goes back to famous work by Abel and Jacobi in the 1820s. Namely, they discovered what are now called elliptic functions. And these are meromorphic functions actually whose periods consist of such a rank 2 lattice. So the original discovery by Abel and Jacobi was that you get these functions as inverse functions of so-called elliptic integrals. And this is very similar how you can get the sine function as an inverse of this basic integral here. So let me talk a little bit about these elliptic integrals. So if you have a polynomial, and of course the polynomials here will have coefficients in the field of complex numbers that has order 3 or 4, and you look at an algebraic function, a rational function in two variables, where you insert for one of the variables here a root of your polynomial, then you call this expression an elliptic integral. Yeah. One can introduce some normalization for these integrals by bringing the polynomial whose root you're taking in some kind of a standard form. And this standard form here, where you have a cubic polynomial with these coefficients here, is a normalization that goes back to Weierstrass, actually. So we can always assume that this polynomial has this form. One can also assume that the roots of the polynomial are all distinct, and this leads to this condition that the so-called discriminant of the polynomial should not vanish. We'll get back to this in a moment. So in order to introduce these elliptic functions, nowadays one does actually not look at elliptic integrals first, but one somehow introduces them directly by some analytic expressions. And in order to set this up, let me fix some notation that I will use for the rest of my talk here. So my gamma is always a rank 2 lattice, and this will be generated here by two numbers that I call omega 1 and omega 2. So they should be linearly independent over R. And I can assume that things are normalized in such a way that this ratio here, which is a complex number but not real, actually lies in the upper half plane, right? So the geometric picture is something like this. I mean, you have your omega 2, you have your omega 1, right? And you get the whole lattice by taking linear combinations of these omegas with integer coefficients. Okay, so this is the basic setup for the rest of my talk. So now let's get to elliptic functions. And a good starting point are these theorems that are attributed to Liouville. Yeah, namely, if you have an elliptic function, a function whose period lattice is such a rank 2 lattice, then the first observation by Liouville is, well, the function cannot be holomorphic, right? So there's no analog really of the exponential or these trigonometric functions that are holomorphic in the complex plane, but you necessarily have to have poles, okay? And then there's another observation, namely if you sum the residues of the poles over such a fundamental region of your lattice, right? I mean, what is this fundamental region? I mean, we have these generators, omega 2 and omega 1, right? And then you can form a fundamental region here that I call F. So if you sum the residues of the poles in such a fundamental region, then you get actually 0. Yeah, I mean, this follows from a simple application actually of the residue theorem. Essentially, you take your elliptic function and you integrate over the boundary of the fundamental region. So if we want to construct elliptic functions, I mean, this then puts some restrictions on what we can expect. So first of all, there's a complication that we cannot avoid, namely, we have to have poles. And the second thing is, well, you cannot have a simple single pole in the fundamental region. So either you have two simple poles with opposite residues, or you can have a double pole, right? So this is somehow what we have to expect. And if one keeps this in mind, then it's somehow easy to try to come up with an expression that somehow resembles these restrictions. Namely, let's try to construct something like this, right? So, I mean, you immediately see that this is cooked up so that if it works, then you get poles at all the lattice points as you should, right? Because if the function has this gamma as its period lattice, then with every pole, you also get poles that you obtain by lattice translations, right? So if, for example, there's a pole at 0, you have to have poles at all lattice points. And this is how this expression is cooked up. And formally, actually, this expression has the periodicity property that we want. Namely, if you add one of your lattice elements to the argument, right, then a simple computation shows that the function doesn't change. Well, there's only one little complication with this whole approach, namely the sum that we wrote down here diverges. Yeah, so I mean, this could work in principle, but not quite in this form. And well, this, of course, was observed a long time ago. And Weierstrass had actually the ingenious insight that by a very simple manipulation, you can actually fix this convergence problem. Namely, he introduced these terms here. And by introducing these terms, you make this expression here actually convergent. Yeah. Now it seems that the doubly periodicity has been destroyed by the introduction of the terms. But if you analyze this a little more carefully, then you see that the function that you get is actually indeed doubly periodic. So it has this gamma as its period lattice. And this expression now is usually called by P. So it's the famous Weierstrass P function. Yeah, so in some sense, it's the basic elliptic function that we have for a given period lattice. Okay, so what can we say about this function? Well, I mean, it's a meromorphic function in the complex plane. It has these double poles at the lattice points. And maybe another important, maybe the most important property of this function is that it satisfies this nonlinear differential equation. So if you take the derivative of the Weierstrass P function and square it, then you can actually express this square of the derivative as a cubic polynomial in the Weierstrass P function itself. And well, in this cubic polynomial, you see certain coefficients classically denoted by little gamma 2 and gamma 3. And these coefficients somehow depend on the lattice and can be explicitly computed, well, if you know what the lattice is, right? So here's this explicit expression where for a gamma 2, you essentially just take the lattice elements that are different from 0 and raise them to the -4. And for the other coefficients, you raise things to the -6. So these sums are the simplest examples of so-called Eisenstein series. And we will discuss this later in more detail when we get to what are called modular forms. Yeah, so these Eisenstein series are the simplest examples of modular forms. Let's now get let's now get to the Weierstrass sigma function. Sorry, the Weierstrass zeta function. So it's a function that is built in a very similar way as the Weierstrass P function. So essentially, we want first order poles now, but in order to get a convergent series, we have to add actually these terms here, so that the whole expression represents meromorphic function in the complex plane. So the relation between this Weierstrass zeta function and the Weierstrass P function is very simple, namely the derivative of the zeta function is just a P function up to a minus sign. Okay. For later on, let me make an important observation. Namely, we can consider this zeta function here as a function of three variables, right? I mean, this variable u, but you can also think of it as depending on the lattice generators, right? So then you get a function that depends on three variables. And you can see by inspection that if you consider the function as a function of three variables, then it has a certain homogeneity property. Namely, if you multiply all the arguments by some non-zero number t, then this number actually pops out as t to the minus 1. Right? So in other words, my zeta function as a function of three variables is a homogeneous function of degree minus 1. So what's the point of this Weierstrass zeta function? Who needs the function? Well, this function actually appeared in Weierstrass's systematic theory of elliptic integrals. So let me just tell you one fact that is somehow related to it. Namely, if we have an elliptic integral here of this kind, where we can assume that this polynomial here has this cubic form, then we want to somehow write this as a function of certain basic elliptic integrals. And in order to formulate a result, let me make the simplifying assumption that all the residues of this expression vanish. Otherwise, if you integrate, you get some kind of logarithmic terms that always complicates things. So if you make this assumption that the integrand of my elliptic integral has only poles with vanishing residues, then one can actually show that such an integral can always be reduced to two basic integrals here, plus some rational function in two variables, z and this root of p. And if you do a substitution, then actually you see that the Weierstrass zeta function appears, namely it appears here from the second term. So in some sense, the zeta function is some of the basic building blocks for elliptic integrals, and this is why Weierstrass introduced this function. So let me state some more properties here of the Weierstrass zeta function that will be important. Right, as we discussed, my Liouville theorems tell me that this Weierstrass zeta function, which has only simple poles at the lattice points, cannot possibly be elliptic. So it cannot possibly have my lattice as a period lattice. But it still has some very good transformation behavior with respect to these lattice generators. Namely, if you add one of these lattice generators to the argument of the zeta function, then a certain constant pops out. Yeah, and these constants, they are called the quasi-periods of the zeta function. So in other words, if you add a lattice element to the argument of the zeta function, well, then you get some additive term that pops out. So if you look at this equation and you use the fact that this zeta function actually is an odd function, then you can write these quasi-periods somehow explicitly in terms of the zeta function and these lattice generators. So one important observation here is, well, I mean, as I said, the zeta function cannot possibly be doubly periodic, right? So this means this eta 1, eta 2, I mean, they cannot possibly be 0. And this is also reflected here in the so-called Legendre relation, right? So the lattice generators and these quasi-periods, they satisfy this kind of determinant relation that if you look at this kind of determinant of them, then you actually get a constant value 2 pi I, right? So this immediately shows that not both of them can be zero. But now let me get to the main point here of my whole talk. Namely, all this shows that, okay, I mean, these quasi-periods eta1 and eta2 of the zeta function cannot both be zero, as we discussed, right? I mean, this can be deduced from either the Liouville theorem or the Legendre relation. But an obvious question that one can ask here is, well, can actually one of these quasi-periods vanish? Yeah, so in other words, can the zeta function for some lattices possibly be a periodic function, right? It cannot be doubly periodic, but can it be periodic? Yeah. My first reaction to this question would be no, it cannot. I mean, the quasi-periods, I mean, should both be different from zero, right? Because it would be weird that for some lattices you actually get a periodic zeta function. But the surprising answer to this question is actually is yes, right? So it can actually happen that one of the quasi-periods, not both of them, but one of the quasi-periods actually vanishes, right? And this is somehow the main point of my talk. So I want to explain to you how this can actually happen and how we can even address such a question, right? How do you study such a thing? And yeah, the basic way to approach this question is to take a closer look again at these quasi-periods, right? So as we discussed, the quasi-periods can be considered as functions of the generators of my lattice. And as we noticed, or as we can see here from the simple computation, they are homogeneous functions of degree -1, right? So if you ever worked with homogeneous functions, I mean, then an obvious thing somewhat to do is look at ratios to make things homogeneous of degree 0. And this is what I'm doing. So in order to study these quasi-periods as functions of my lattice generators, I look at this quotient P here of eta1 and eta2. And this now is a homogeneous function of degree 0. So this actually means that I can consider this as a function of the ratio of omega1 and omega2, right? So in this way, I get a P that is now a function of one variable. And in order to study the zeros of eta1 and eta2, I can now study the zeros and poles of my P, right? Because the zeros of eta1 correspond to the zeros of P. The zeros of eta1 correspond to the poles of P. So now I'm reduced to a much more classical question. I have a certain function. It will actually turn out that this function P here is a meromorphic function. And I am trying to understand the zeros and poles of this function. As you will see later in my talk, this function P actually admits a very explicit geometric description, and this will be formulated in the main theorem of my talk. So this is the main point that I want to make. One can actually precisely say what this function P is as a function of this ratio of the lattice generators of this variable tau. Before I get to this, I have to point out an important property of my function P. Namely, it has a certain, well, equivariance property. Namely, let me take integers that satisfy this determinant relation. In other words, A, B, C, D can be thought of as the coefficients of a matrix in SL2Z. And let me change my lattice generators by the corresponding transformation that I get out of this matrix. Well, as you probably all know, if you apply this transformation to the generators of the lattice, then the lattice actually will not change, right? So in other words, the zeta function that I get will not change. But these etas actually will change because they not only depend on the lattice, but also on the choice of the generators of the lattice, right? So if I have new generators, then I will get new etas. On the other end, I can use the old generators to compute this new eta. If you do this simple computation, then you see that the new eta is related to the old etas by exactly this kind of matrix with exactly the same coefficients, right? And this means if you look at the ratios of these etas, then you get a curious property of your function. Namely, it has this kind of equivariance property that I'm aiming at. Yeah, so if you feed into your function p such an element of the so-called modular group, right? Then actually this element of the modular group comes out of the function unchanged, right? Or if you want to write it in a more elegant form, you have this kind of property. If you feed in any element of the modular group, then this element just pops out, right? So you have some kind of commutation relation between elements of the modular group and the function p, right? So you can write this explicitly for generators of the modular group. So you get this relation. And this, for example, tells us already something, namely, if you want to study the zeros and poles of p, then it's actually enough to study the poles of p, right? Because you see that if you have a pole of p here, well, then you get a corresponding zero, right? So if you want to understand where these etas vanish, I mean, then it's essentially enough just to study the poles of p. So I'll come back to this equivariance property later on. So this will be very important in my explicit description of these p's. Let me say a few words about the history here. So this function p, of course, I mean, has been known for a long time and has been studied. So for example, there is a paper by Watson from 48 where he investigated the poles of this function p. And he noticed, and this is really a very simple observation, that there is a pole on the positive imaginary axis, and Watson actually computed this zero to great accuracy. Then later, Heinz actually also studied this function p, and he proved that it has infinitely many zeros and poles in the upper half plane. What Watson and Heinz both missed is that this function p is, as we will see later, admits a very simple geometric description that is, for example, immediately tells you that the function has to have infinitely many zeros and poles in the half plane. Right, so Heinz actually proved this theorem not by somehow having an explicit description of the function p, but he used some actually very clever function theoretic methods to prove his result. So before I get to my main theorem, there's something else that we have to discuss before we get there. Namely, let's get back here to our Eisenstein series. Right, so remember, they somehow turned up in the coefficients of the differential equations for the Weierstrass P function for a given lattice. And nowadays, often one doesn't write them in this form, or one doesn't study them in this form as homogeneous functions of two variables, but one rather introduces a normalization so that one gets functions only of one complex variables. And these functions that one gets in this way, if one introduces this normalization, they're nowadays called E4 and E6, right? And well, I mean, one can explicitly write these functions here, for example, in the so-called Q expansion, right? So there will be one periodic functions, and one essentially can write an explicit Fourier series for these functions. And you get these kind of expressions here where, well, if you work this out, I mean, you get certain Fourier coefficients here that are related to these so-called divisor sums, right? So for E4, you look at the cubes of all divisors of a given integer, and for E6, you look at the 5th power of all the divisors, and you sum this up to get these kind of coefficients. So these functions are the simplest example of what are called modular forms. So these functions here, a function of 2 variables, they are often called homogeneous modular forms, while these functions here, these functions of 1 variable, are called inhomogeneous modular forms. So it has some advantages to work with either homogeneous or inhomogeneous forms. So homogeneous forms have the advantage that the transformation properties of the forms are somehow immediate, right? I mean, if you look, for example, at this expression, then it's clear that this expression doesn't change if you use different generators of your period lattice, right? Because the expression that defines this G4 only depends on the lattice and not on the specific choice of the generators, right? So
there is a question in the chat.
Well, the relation between Q and tau is just this relation, right? So Q is e to the 2 pi I tau. So that's some very standard notation in this context. Okay, so let's move on here. I need one more expression of a similar type. My iPad is not acting up here. Oh, no, here we go. Right, so yeah, this here summarizes what I already said in words. So this G4, for example, is a homogeneous modular form, right? And we saw this gamma to the -4. So this means it will be a homogeneous function of 2 variables of degree -4. And this other property that I mentioned is, well, I mean, if you change the lattice generators, then the expression doesn't change because it's an expression that just depends on the underlying lattice, right? And if you translate it into formulas, I mean, you again see essentially some nice property with respect to the modular group. This can also be translated to the inhomogeneous versions of these modular forms. And well, then you get essentially these relations here for the generators, right? So if you look at the full modular group, I mean, then these expressions, I mean, the transformation behavior looks a little more complicated. But if you write it for the generators of the modular group, I mean, this translation by 1 and this kind of inversion here, then you get some very nice and simple looking expressions. There's one more expression of a similar type that I need. And this function is traditionally called E2. And it's not a modular form. It's a so-called quasi-modular form. So it still is 1 periodic. But now if you feed in this kind of inversion into the function, then you get an extra term here that pops out, right? I mean, if it was a modular form corresponding to weight 2, I mean, then you would just have this tau square here, but you get this extra term. You can also write this E2 again as an explicit Fourier series, where of course Q is again e to the 2 pi I tau, right? And then you see actually this the sum of the divisors of your n here, right? So well, I mean, this quasi-modular form has been known for a long, long time. I mean, number theorists study this a lot. Actually, one of my colleagues, Bill Duke, says that this is his favorite function in mathematics, this E2. Okay, so let's move on here. So why am I introducing these functions? Well, the reason is analytically, it's very simple to somehow express my Adas in terms of this quasi-modular form E2. And these are the basic formulas here. It's hard to say who first discovered it. I think this goes back all the way to Weierstrass when he introduced his elliptic functions. So these formulas are well known. And they actually give us an explicit expression of this ratio that we're interested in, right? The ratio of these Adas. Namely, we can write it in a very simple form. in this way here. Right? So what this actually means is that if we want to study the poles of P, then all we have to do is actually study the zeros of this E2. I mean, this would be one way of doing it. This is actually, for example, how Watson found his zero. You know, if you look at the Q expansion of E2 again, so if you analyze this, I mean, then it's very easy to see that actually on the positive imaginary axis, you will have to have a zero, right? I mean, on the positive imaginary axis, this Q actually is a real number between 0 and 1. And it's very easy to see that if you run from somehow infinity back to 0, I mean, then this expression is monotonic. It starts at 1 and drops to minus infinity. So there has to be a 0 on the positive imaginary axis. And you can actually use this expression then to compute this 0 with high accuracy as Watson did. Okay, so let's move on here. This. So in order to formulate my main theorem, I need one more thing here, or I need a couple of more things. Namely, it's not hard to compute some special values of my function P, namely for certain lattices that have a nice additional symmetry properties that not all lattices have. And well, so one thing that you can observe is some asymptotics, right? So if you let the imaginary part of tau, the ratio of the lattice generators, go to infinity, I mean, then Q goes to infinity, and then E2 goes to 1, and this actually leads to this relation. So that if you look at infinity, then P maps infinity to infinity. The other thing is, and I will not justify this in detail, is that if you look at some lattices, as I said, with extra nice symmetry properties, for example, the integer lattice, then you get some relation between these etas, and this allows you to compute their ratio. And well, in this way, you can show that the value of P at I actually is minus I. And a similar thing here happens at this root of unity. Yeah, so you can show that it's at this root of unity that I call a rho. Again, my function can be computed explicitly, and you get the complex conjugate of rho. And what this means is actually this. So if I look at not P, but the conjugate of P, then I get a function that fixes infinity I and rho. Right? So this is a kind of curious property. And I will try to explain to you how this can possibly be. And for this, I have to remind you of this famous tessellation of the upper half plane that you get essentially from the action of the modular group, right? So this triangle here, this T naught, is essentially a fundamental region or half of a fundamental region of the modular group. Often it is useful to throw in an extra element into the modular group, right? The modular group consists of these Möbius transformations, but let's throw in the reflection here in the imaginary axis. So then you actually get a group that is slightly larger than the modular group. I mean, the modular group sits inside this larger group as an index 2 subgroup. And the group now that you get is actually generated by the reflection in these sides of this fundamental triangle T naught. Yeah. And a curious thing now happens, namely, if you look at our function P, so I formulated this equivariance property of P. So if you translate this into this geometric picture, then you can notice that actually P, and hence also this conjugate of P, undergoes exactly the same reflection that you get if you start reflecting here in the sides of this triangle. So in other words, if you reflect the argument of P, let's say in this side, then the value will actually undergo exactly the same transformation. So this is this equivariance property translated into this geometric picture. So yeah, so let me summarize. So my P function, or the complex conjugate of the P function, fixes these 3 points here, I, this rho, and I infinity. And it undergoes exactly the same transformations that the argument undergoes if I start reflecting in the side of my T naught. Right? So how can this possibly be? Is there some kind of a natural function that has this transformation behavior? And the answer is yes. And let me try to convince you of this. Namely, let's look at a slightly more general situation. So we have some circular arc triangle, right? The circular arc triangle, this T naught that I introduced, has angle 0, pi over 2, and pi over 3. And it turns out that if you have this situation, then there is a natural triangle associated to this T that I call the complementary triangle. And in the picture, I mean, it's just this this triangle that you get from the lune in which a T sits, right? So T and T prime, this complementary triangle, share 3 vertices. They have exactly the same vertices. And they actually are also, their sides actually are also arcs on exactly the same circles. I mean, so you see, I mean, this arc here, my triangle T, if you continue it, I mean, then you get this arc. So it's an arc on the same circle, not the same arc, but an arc on the same circle. And what this essentially means is the following. So if you start reflecting this triangle T in either of the sides, then the triangle T prime will undergo exactly the same transformations, right? Because you reflect exactly in the same circles. So in other words, this relation between T and T prime stays fixed. Yeah, so T prime will undergo exactly the same transformation as T if you start reflecting. So let's look at our situation here, where we have this fundamental triangle of the modular group that I call T naught. Is there some kind of associated triangle that undergoes exactly the same transformation if you start reflecting? And the answer is yes. Namely, just let's look at this triangle below here. Right? I mean, it's in this sense the complementary triangle of my T naught. Okay. So another observation is, this observation leads to a natural question, namely, could our P be somehow related to this triangle T naught? Is there some kind of a natural conformal or maybe anti-conformal map that is suggested by this picture? And the answer is yes. Namely, suppose our P here is an anti-conformal map, or let's look at the complex conjugate. Suppose this is some kind of an anti-conformal map that behaves like a reflection. All right, so it somehow maps T naught into this triangle. Then first of all, my map would fix these 3 vertices, right? And moreover, it would have this kind of equivariance property that that I expect from P, because if I start reflecting in any of the sides here, then the image would undergo exactly the same transformations, right? So this geometric picture somehow suggests that maybe my function P, or this P bar function, is exactly a conformal map from this triangle T naught to its complement. And that's actually my main theorem. Yeah, so it's formulated here. It looks a bit technical, but the way to think about this is really just in this geometric picture. So my map P here maps, or rather the complex conjugate is really a conformal map or anti-conformal map from this T naught onto its complementary triangle, so that these vertices are fixed. Yeah, so this is what this here says in geometric terms. So maybe I should ask you at this point whether there are any questions. So that's the main theorem. And now the question is, I mean, how do you prove something like this, right? So we haven't somehow a candidate for what the map should do. Well, how do we establish this fact? And well, in order to tell you how you go about this, I have to talk about one more thing, namely the so-called hypergeometric differential equation. So this is a second order linear differential equation where you see some parameters here. And this is closely related to what is called the Schwarzian derivative. Namely, one can show that if you take a fundamental, if you take a fundamental solution of this differential equation and look at the ratio, then this ratio actually has a Schwarzian derivative that can be explicitly computed from the coefficients of the hypergeometric equation, right? I mean, so these lambdas, mu, nus here are certain expressions in the alpha, beta, gammas. Conversely, one can show that if you look at any solution of this nonlinear differential equation, well, it always arises as such a ratio of a fundamental system of solutions of the hypergeometric equation. So this is something that has been known for a long, long time. I mean, it goes back essentially to, I don't know, I mean, I think some cases were even known to Gauss. But there's a famous paper due to Schwarz, namely he studied the geometric properties of these ratios, and he found that actually, well, if the coefficients of the hypergeometric equation are real, then this ratio has a very nice description as a conformal map. Namely, it maps the upper half plane conformally onto an circular arc triangle where you can compute the angles of the circular arc triangle explicitly from the coefficients of the hypergeometric equation. So I should maybe back up here and say one more thing about these angles that I expect, right? So if I mean, the picture here got kind of cluttered. So if I look at the angles, right, that my conformal map should have, well, then I have a 0 angle here. Here I have a pi over 2 angle that should be preserved by my map. Here I have a pi over 3 angle, and the complementary angle here is 2 pi over 3. Right, so my triangle T naught, the fundamental region of my extended modular group, has these angles 0, pi over 2, pi over 3, while this image triangle here has these angles 0, pi over 2, 2 pi over 3. Right? So this actually gives us these coefficients alpha, beta, gamma, right, that my solution should satisfy, and this gives me a strategy for the proof of the main theorem. So let me use the 2 minutes or so that I have here to outline the strategy, right? So our map that we want to discuss, I mean, this P maps a circular arc triangle to a circular arc triangle. So this does not immediately fit into this framework that Schwarz studied. So what we should do is we should look at an auxiliary map that maps this T naught to the upper half plane, right? And we should consider our P as a variable of this new J here that now lives in the upper half plane. And then we could try to compute the Schwarzian derivative of P with respect to this new variable J and show, you know, that it corresponds to a Schwarzian derivative that has the right type of angles, 0, pi over 2, and 2 pi over 3. Another approach is we can maybe try to express our T as a ratio of two solutions of the hypergeometric ODE with this variable J and these coefficients that we need to get the right angles, right? And well, you can actually do this, and for this, you somehow have to differentiate this function E2 that gives me the analytic expression that I need. And it turns out actually there are some very nice and explicit formulas for these derivatives that are relevant, namely the derivative of my quasi-modular form, then also the derivatives of these Eisenstein series. So these formulas are often attributed to Ramanujan, but actually they are much, much older in disguise. I mean, they already appear by Weierstrass. So this function J actually that maps my fundamental region to not to the upper F plane is also explicitly known. So it's called it's the so-called absolute invariant, and it can be expressed explicitly in terms of Eisenstein series, right? And this actually means you can do all these computations explicitly. I mean, I have to gloss over this a little bit because I'm running out of time. For example, I mean, you can compute the derivative of this new variable J in terms of tau, and you get some explicit expression where this J appears and this discriminant, right? And you can also introduce auxiliary functions whose ratio is this P function that you want, and then do explicit brutal computations. And you can show that actually these auxiliary functions satisfy exactly the hypergeometric differential equation that you want. So it has this form here, and it's actually not new. It was already discovered by Fricke-Klein, but they failed to point out what you actually get geometrically for this function P, the ratio of these auxiliary functions. Right, so if you work through all the details, I mean, then you actually get a proof of the main theorem. Let me just mention here in passing that you can also do the same thing based on Schwarzian derivative computations. I mean, the computations get really, really nasty. With a student of mine, Zach Smith, we tried to use some computer algebra program for this, but we had to work quite hard actually to convince the program to do these kind of Schwarz derivative computations. So let me finish my talk here by making some additional remarks here. Once you somehow know what the function should do, you can also somehow give a much more elementary proof based on the argument principle. But I think this ODE approach, going through the hypergeometric equation or the Schwarzian derivative, is a more systematic approach because it also applies to some other situations. Yeah, I should mention that my talk actually was motivated by a question that Alex Eremenko asked me. So he asked me, whether these differential equations, these ODEs, can also be computed for periods of some other elliptic integrals. And in some sense, I mean, I observed that the simplest case of all this is this P function that we studied, right? Maybe another thing that I should point out here is that is another kind of direction where you find functions with very similar equivariance properties with respect to the modular group, namely they arise as Thurston-Pullback maps, right? And this somehow suggests that there is a relation of these type of functions with modular forms, but this has not been studied at all. So I think this would be a very interesting topic for further exploration. And with these remarks, let me finish my talk because my time is up. Yeah, thank you.
Okay, thank you, Mario, for the very nice and intriguing talk with lots of different ingredients. So any questions? All right, let me maybe then ask a few questions. I don't like, I mean, in this last remark that you made, so what kind of things do you expect? I mean, what kind of relations do you expect, like to?
Yeah, look, I mean, it would be kind of nice to be able to write some of these Thurston-Pullback maps explicitly in terms of these basic modular functions. Yeah, I mean, I think this is more than a kind of silly exercise because you can then translate this into some geometric moduli problems. Yeah, so I think that's something that somebody should look into.
Okay, and I know, like, I mean, I was always curious. I mean, like, so this, I never kind of looked explicitly at this, I mean, at this modular forms topics, but I mean, this kind of constants that appear, I don't know, for instance, in this J invariant. So do they have like special meaning? I mean, so, I mean, like, So where do this, like 1,728 comes from? So I mean, like, is
This?
there, yeah, I mean, like, is there any meaning to this? I mean,
Well, I mean, this is something that number theorists have been studied like crazy. For example, there's a famous conjecture here about the Fourier coefficients of this modular form J. And, this is related to what is called moonshine. So there are some funny numbers that pop up in the representation theory of the so-called monster group. And some are mysteriously the Fourier coefficients of this J function, or some are related to this. This was explained by Borchardt, and this is why he actually got the Fields medal. Yeah, so sure, I mean, these modular forms have a huge number theoretic significance.
all right. Any other questions? Okay, if not, then let's thank Mario again.